picking up where we left off last time, today first we're going to talk about the pn-Junction. We're going to dive into the actual operation of the pn-Junction. But last time, what we had talked about were semiconductors in general. We talked about the lattice structure of a silicon crystal and how we have a situation where the silicon atoms have an outer shell with 8 spots and they have 4 valence electrons, and so they form this pattern, this lattice with other surrounding silicon atoms using covalent bonds, and they form a more stable structure. Then we talked about doping, and so doping was the introduction of these impurities. And the impurities, the examples we used were boron and phosphorus. They have a different number of valence electrons, either 3 or 5. And by introducing these impurities to the lattice structure, we free up some charge carriers for current conduction. We went through some examples and talked about how to calculate various values for these semiconductors, calculate conductivity. And then we also talked about 2 different types of current. And so these 2 different types of current are going to be very important for our discussion today. The first type of current that we talked about was drift current. And so drift current is a value that falls in line with our traditional look at current, right? Ohm's law says that the value of current is proportional to the voltage being applied. And so drift current is that which is excited by an electric field or an electromotive force. It's dependent on several different values, one of which is a value we call the hole mobility, or the hole or electron mobilities. Diffusion current was a little bit different. So diffusion current is not dependent on an applied electric field or electromotive force, at least not directly. It works like diffusion of any other chemical or any other atom or particle, right? So what we have is a whole bunch of electrons, free electrons on one side, very few on the other side. We have a large gradient, and so a diffusion force will push the charge carriers to even out that concentration gradient. So drift current, diffusion current, we talked about both of them last time, and we'll see that they both come into play when we talk about the structure and the operation of a pn-Junction. So now moving on to the pn-Junction, we're first going to talk about the pn-Junction with open terminals or open circuit condition, meaning that we haven't applied any voltage to the pn-Junction. And then we're going to go on to the forward bias and reverse bias cases where we are applying a voltage. So what is the state of the pn-Junction with open circuit terminals? The p-type material contains a majority of holes, that's the majority charge carriers, and the n-type material contains a majority of free electrons, again the majority charge carriers. However, these majority charge carriers are neutralized electrically by an equal number of bound charges. These bound charges come from the environment, and they have very specific properties that we're going to talk about once we get into the discussion. Essentially, the bound charges don't act like our majority charge carriers. They aren't subject to diffusion forces, and they don't recombine with other particles nearby, right? Initially, we would expect that these available holes and the bound negative charges, they should be attracted to one another and recombine, but they don't. I encourage you to read the book. Ch03 does a great job of explaining this. I also think this is a topic that is best explained, one pass through in lecture and another pass through reading it. But we're not going to go into all the details of how bound charges work, or more specifically, all the details of why bound charges act the way that they do. Certain parts of this chapter you do have to take at face value because of the limitations on how deep we have the time to go to dive into the physics and the chemistry. So what is a bound charge? It's a charge of the opposite polarity to one of our majority charge carriers. It neutralizes that electrical charge. It does not affect the concentration gradient, which we'll see in a second. It's not subject to diffusion force. It does not recombine with the majority charge carrier. It's one example or analogy I often give is it's sort of like the icing on a cake. Okay, it's there, it's close by, but the icing, right, can't go into the cake. It's just sort of this layer that lays on top. So what happens when a p-n junction is newly formed and the p and the n-type semiconductors first touch one another, first come into contact? So first thing we have is, we can see this picture here. We have our n-type semiconductor, our p-type doped semiconductor. We have a lot of majority charge carriers on either side. In this picture, the minority charge carriers are not shown because the numbers of them should be very small. The smaller circles represent the bound charges. Okay, so we have negative bound charges on this side and positive bound charges on the other side. And again, these charges are weakly bound to the majority carriers and they do not recombine. We've already said that before. So what happens when you first put these two together? This is a snapshot of t equals 0. What happens at t equals greater than 0? So forget about the bound charges for a second because we already said that they don't recombine, they're not affected by diffusion force x, y, z. Let's talk about the majority charge carriers. Yeah.
So there's like a region that's going to form in the middle where
Yeah.
they combine together.
Exactly. So skipping ahead a little bit, the first part of that process is noticing that there's a huge concentration gradient, right? So the concentration gradient you have is a lot of pluses and then almost no pluses. Again, these don't count as part of our concentration gradient. A lot of negatives and then no negatives. So the diffusion force pushing the holes to the right and the electrons to the left is going to be pretty large. So diffusion will begin. The free electrons and holes closest to the junction will cross over to the other side, and most of them will recombine. And what the result of that is a whole bunch of uncovered bound charges inside of this middle region that we call the depletion region. Depletion region because it's depleted of all the majority charge carriers. So why does diffusion occur even when the bound charges neutralize the electrical attraction of the majority carriers to one another on either side? The answer to that, right, is that diffusion has nothing to do with electrical attraction anyway. So the fact that the bound charges electrically neutralize the majority carriers does not stop the diffusion. And so the diffusion continues and slowly evens out the concentration gradient. Now, the uncovered bound charges in the depletion region, let's talk about them for a second. These are all electrically neutralized. These are all electrically neutralized. But now, these, they lost their partner. So what we see is a barrier voltage does build up in the depletion region as a result of the uncovered bound charges. And so this barrier voltage will get larger and larger as the number of particles in the depletion region increases. So it starts out at 0, diffusion starts, uncovered bound charges, more uncovered, on and on, until eventually we reach an equilibrium value, and we'll talk in a minute about what will cause us to reach equilibrium. The final value of the barrier voltage we call the built-in voltage. Okay, So now, the new thing about this picture is the arrows at the top here. So we see there's two red arrows. We know that the diffusion current affects a net flow to the right, meaning that we have positive particles moving to the right and negative particles moving to the left. Remember that our definition of current is actually the opposite of the direction of electrons. So this is diffusion. Next, minority drift current. So what is this describing? If you look here, you will see that the polarity of this voltage is such that it will sweep any minority charge carriers that are close to the edge across to the other side. Okay? Right? This polarity opposes the diffusion, meaning it doesn't want to allow the positives to go here and the negatives to go here, but it reinforces the minority charge carriers because they have the opposite sign. Now, if we go back and let this little animation thingy run one more time, you'll see that the drift current the magnitude or the length of that arrow, which represents the magnitude of the drift current, it doesn't change. And we'll talk in a minute about why that is. But the length of the diffusion current, or the length of that arrow, does. Because as diffusion occurs, right, it evens out the gradient and essentially reduces the diffusion force, right? As diffusion occurs, the catalyst for diffusion force goes down. And so what causes an equilibrium is not IS increasing and ID decreasing. It's simply just ID decreasing. IS has a set value, and ID falls until it reaches IS. So this built-in voltage opposes the majority diffusion current, and when those two forces are equal to each other, you reach the equilibrium, and you're essentially done as far as the open circuit condition is concerned. So once the equilibrium is reached, the magnitudes of the diffusion and drift currents equal one another, and the result is no net flow. So now, let's talk a little bit about the built-in voltage. So the pn-Junction built-in voltage is the equilibrium value of the barrier voltage, or the final value of the barrier voltage. So it's defined to the right in equation 322. And so what you can see is that it's equal to the thermal voltage, which is a value we defined earlier on in chapter 3, if you remember when we talked about the Einstein relationship. Generally, it takes on a value between 0.6 and 0.9 volts for silicon at room temperature. Considering the fact that the pn-Junction is the diode, does that value seem familiar at all? If you remember, when the diode is in the forward bias region or is conducting, the voltage across it was approximately 0.7 volts. And that relates directly to the value for the built-in voltage that we see here. The thing about this is that the voltage is applied across the depletion region, not across the terminals of the pn-Junction. So this built-in voltage, you can't measure it with a DMM. You can't draw energy from it or anything of that nature. Okay. So now let's talk a little bit more about the drift current IS and how it contributes to equilibrium. We've said very briefly that the drift current is associated with the flow of minority charge carriers, and it's affected by the built-in voltage, right? Hence why it's a drift current and not a diffusion current. So some of the thermally generated charge carriers in both the P and the N-type materials will move towards and reach the edge of the depletion region as part of the process we were talking about previously. Once they reach the edge of the depletion region, the built-in voltage, or the barrier voltage, causes them to be swept across to the other side. Now this is the reason why the length of the IS arrow doesn't change as VO gets larger and larger. There's no resistance or very, very minimal resistance in the depletion region to the flow of the minority charge carriers. So any voltage, any really small built-in voltage is enough to sweep them over to the other side. Unlike diffusion current, right, the polarity of VO reinforces the drift current of the minority charge carriers. So then one would ask, well, what determines the length of that IS arrow? It's not the magnitude of V naught. Something must determine it. So it's dependent on the real limiting factor, which is the availability of the minority charge carriers. Okay? The IS value is limited by the small number of thermally generated minority charge carriers that we have. So therefore, IS is not dependent on V naught, but it is dependent on temperature. So as temperature goes up, you would expect more thermal energy in the lattice structure, more minority charge carriers to be produced, and IS gets longer. So again, any depletion layer voltage, regardless of how small, will cause the minority charge carriers to be swept over to the other side, and this is the main mechanism that causes our drift current flowing from right to left. And so here is a similar, we've seen that already a couple times before. Okay, now, a couple of other questions. As we get more and more familiar with the pn-Junction, let's ask the question, is the depletion region always symmetrical? Is it always the same width on either side? And the answer to that is no. And the reason why is because the real limiting factor is that the amount of charge on the left-hand and the right-hand side needs to be equal. If we have 4 electrons on the left-hand side, we need 4 holes or positive charges on the right-hand side. It needs to even out. And that makes sense because it's created by the majority charge carriers canceling out. So one uncovered bound charge is only created when another uncovered bound charge is created. So if we have a higher doping concentration on one side than the other, what we'll end up with is a lopsided depletion region. The depletion region will extend further into the area that has a lower doping concentration. If we have on one side, well, there's a picture that demonstrates this idea much better than how I can describe it. This picture. So if you look at this picture here, right, it shows that on the left-hand side we have a higher doping concentration. We only require one column in order to capture 6 uncovered bound charges, whereas the doping concentration on the other side is lower, and therefore it takes 2 columns or double the amount of width to get our 6 charge carriers. But again, the equality that we're looking for is charge. The absolute value of the charges are equal to one another. And these variables here, xp and xn, they will describe the width of the depletion region on either side. xp on the P side, xn on the N side. And you can see those variables are shown here on the bottom, xn, xp, and then we consider x equals 0 to be the center of the junction. So anything on the P side is negative, anything on the N side is considered to be positive. So this picture shows that the most important way to look at the depletion region is in terms of charge. And so you see this graph here. What it says, on the x-axis we have x. On the y-axis we have charge, it says change, but charge density. Okay? And so on the left-hand side where we have a higher charge density, the width is less. On the right-hand side where we have a lower charge density, the width is wider. But the area inside of both of these rectangles is the same, which denotes that they contain the same amount of charge. We can also calculate from that graph the voltage that would associate from that charge, and it would look something like this right here. We've been mostly using a straight line to represent the built-in voltage, but that shape is more representative. Okay, now how do we define the charge stored on both sides? Equations 323 and 324 take care of this for us. So 323, 324 say that the absolute value of the charge is equal to the charge of an electron times the cross-sectional area times the width of the depletion region on either side times the concentration or the number of doping atoms. Now, we know that this should be equal to this in order for equilibrium to be reached properly. And so with these equalities, right, we can knock off the A's, we can knock off the Q's, and what we're left with XP NA equals XN ND. And then what we can do is turn that into equation 325, which shows us what we have already sort of said, which was that the depletion region will extend further into the less doped region and will be shorter on the other side. So this equality just demonstrates that. Okay, there's a couple other equations here that are taken from the text. I'm not going to go and give derivations for each one. They do for some of them in the book, but it's probably not the best use of our time. And really, we're going to be just using them. We're just going to be applying them predominantly. Okay, so equation 326 tells us that the width of the depletion region equals xn plus xp. No duh, right? Of course, the width on the x side, the width on the n side plus the width on the p side would equal the total width. And this equation here gives us another way of defining that. So it's equal to the square root of 2 times epsilon s, which is the electrical permeability of silicon, all right, divided by the charge of an electron. Can you do me a favor? The whispering in the back, I can really hear it. Sorry. It's like trying to talk on top of like a radio playing. No problem. So 2 times the electrical permeability of silicon over Q times 1 over Na plus 1 over Nd times the built-in voltage. Okay, and so we can also take this version of the equation and turn it into 327 and 328 down below. All this says is that the width on the n and the p sides is proportional to W, and then the ratio of the concentration, the doping concentration values. So this chapter, I think I've said it several times before, I'll say it one more time. The way that we test this chapter is going to be a little bit different than chapters 1 and 2. The math in this chapter is relatively easy, but that being said, there's a lot more concepts and terms that you have to understand. Obviously, we've been going through some of these like mini animations and sort of talking about how the process occurs. You do have to have an understanding of that. And then lastly, there are going to be equations like these, a lot of them not necessarily sharing that many values with one another, that you have to know how to implement. Remember, this is a constant, and what Na and Nd are and V naught. So again, it pays. When we eventually get to the midterm that deals with this material, you should be looking at the cheat sheet and make sure that you understand all the equations that are on there. We can take 326 through 328, and we can give another version of our Q sub j, which is the charge stored on either side of the depletion region, and that will be equal to A times Q, and then this, as well as this version down here. Again, I'm not going to go into derivations, but we've already explained what each one of the values are, and so you should know how to implement that. Okay, so what have we learned about the pn-junction so far? I think we have a pretty good understanding of the way that this thing works when it's open circuited, when nothing is attached to it. So first things first, composition. The pn-junction is composed of two silicon-based semiconductors, one p-type doped, one n-type doped. They're put together. There's a junction in the middle. There's terminals on either side, right? Majority charge carriers are generated by doping. The holes are present on the p side. Free electrons are present on the n side. Again, nothing new there. The bound charges. They neutralize the majority carriers. They have some very specific characteristics. Again, they don't recombine with the majority charge carriers. They don't affect the concentration gradients. And we've talked about that already. The diffusion current, right, is applied to the majority charge carriers. What we see is that when we initially put the two sides together, we have a huge concentration gradient. A lot of one on the other side, none, a lot, and none. So there's a lot of diffusion force that's trying to push that towards the center, push those majority charge carriers towards the center. That diffusion force, what it does is it causes the majority charge carriers to go, they move to the center, they meet one another, and they disappear or they recombine. So as the charge carriers recombine, they release the bound charges or uncover the bound charges. And so inside of the depletion region, although we don't have any majority charge carriers, we do have the uncovered bound charges, which causes this built-in barrier voltage to appear. And so the value of the depletion layer voltage will be dependent on when equilibrium occurs. Minority charge carriers, there are still minority charge carriers in the pn-junction. Like any other case, they will be thermally generated. That'll be free electrons on the p side and available holes on the n side. And so we talked about what caused diffusion current, but there is also a small drift current that will be flowing. The drift current is going to be affected by the built-in barrier voltage and applied to or cause the movement of the minority charge carriers. And so the equilibrium occurs when the diffusion current drops to the point where it's equal to, but has the opposite direction of IS. And IS, again, that value does not change with V naught. It's limited predominantly by what? I think we said this once or twice. What limits IS? Temperature is what affects it. That's 99% of the answer. The last 1% is temperature affects it because it's limited by the minority charge carrier concentration, which we have very little of, and we know that temperature is what can cause that to go up and down. Okay, so now we have a pretty good understanding of the open circuit condition. Let's move on to the more interesting cases of forward and reverse bias and how this thing works. So first things first, what determines which direction is forward and which direction is reversed? Essentially, it has to do with whether the voltage we apply reinforces V naught or works against V naught. So if the polarity of the voltage we apply reinforces V naught, then we're talking about the reverse bias case. If the polarity of the voltage we apply is opposite or works against V naught, then we have forward bias. So we'll call any reverse bias voltage VR. We'll call any forward bias voltage VF. So to compare these three cases, okay, open circuit, reverse bias, forward bias. No voltage applied. VR has the same polarity as V naught. VF has the opposite polarity of V naught. Voltage differential across the depletion region is V naught. Voltage differential across the depletion region will be V naught plus VR. They reinforce one another. Voltage across the depletion region is V0 minus Vf because they work against each other. ID is equal to Is. We know that from our equilibrium. ID is less than Is. The diffusion current is less than the drift current because by expanding our depletion region, or reinforcing our depletion region, we're further creating a boundary or a resistance against diffusion. So what we see is that IS is the same length in all three of these cases, again, as we would expect, but ID becomes smaller. So for the reverse bias case, we normally, as far as the ideal model is concerned, we think of that as blocking. But if for those of you who have seen the diode in lab, it does conduct a very small reverse direction current, and so that would be equal to IS minus ID. But again, there's only so big this can become because IS itself is very small. So, right, if this is 1 nanoamp, even if you subtract 0 from it, you're still only left with 1 nanoamp. For the forward bias case, now ID is much larger than IS, and the sky is the limit here, because ID can become very large. And the reason why ID grows is because now our VF is reducing the barrier to diffusion. So that's the basic idea behind the operation of the PN junction, is that a reverse bias voltage increases the barrier to the diffusion current ID, and a forward biased voltage reduces, sorry, I don't know if I said that right, this reduces the barrier to the diffusion current. And so if I had to describe the way that the PN junction works in 2 or 3 sentences, that's really the most concise description. All right, so now that we've talked about those mechanisms, let's see how they affect some of the equations that we've already defined. So you remember this equation? We just talked about it like 5 minutes ago. So this gives us the width of the depletion region in terms of the voltage across the depletion region. When we had the open circuit case, it was just V0. Now we're going to replace that with V0 minus Vf. We can also do the same thing down here when we talk about the charge stored in the depletion region. This, the permeability, charge of electron, doping concentrations times VO minus Vf. So you can see the width of the depletion region getting smaller, again, which you've already seen in the pictures. If we replace the voltage across the depletion region with V0 plus VR, then the width of the depletion region gets wider. We'll have more charge stored on both sides of the junction, and we have already seen that acts as a barrier against our diffusion current flow. Okay, so I think we've done a good job so far of talking about the math and how the forward or reverse bias voltage affects the numbers. But it's probably not 100% clear yet exactly what's going on inside of the PN junction and how are we getting current from one end to the other. And exactly, okay, we said, all right, VF works against the built-in voltage and VR reinforces it, but why exactly does that have the effect that it does? So let's take a little bit of a closer look. So in this picture right here, we're going to use a little bit of a different notation. And what I mean by that, so the bound charges are shown in the middle. We're not going to be discussing those anymore. We're actually going to take them out of the picture. The small circles now, instead of representing the bound charges, they represent the minority charge carriers. Hence, that's why there's no longer a one-to-one relationship. Okay? There are fewer. Now, this is not a very good example of the actual ratio because in reality it would be multiple orders of magnitude smaller, not 1, 2, 3, 4, 5, 6, 7, 8 versus 4. That's obviously that ratio is off. But for the purposes of demonstration, I think this works well. So we're going to get rid of the bound charges. We're not even going to talk about those anymore. And so what happens when we apply a forward bias voltage? So a forward bias voltage, you'll see this is the negative end of the EMF, which then will repel the negative majority charge carriers. The positive will also repel the positive. So not only does it decrease the voltage across the depletion region, because these, you can consider them being in series, right? So the voltage here will be the subtraction of the two. But it also pushes the majority charge carriers towards the center. And so as VF increases, the depletion zone becomes thinner and thinner, such that that barrier can no longer stop the diffusion from one side to the other. So applying VF essentially undoes the equilibrium and starts up this engine again, allowing diffusion from one side to the other. Now in this case, the diffusion will be, the magnitude of it will be more significant. Not all of the charge carriers are going to recombine because it'll be occurring at a higher rate. And so some of the majority charge carriers will actually reach the other side, okay, and will become what we're going to call new minority charge carriers. Because even though they started out as majority charge carriers, once they end up on the other side, now they're part of the minority, right? A minus over here is a majority, a minus over here is a minority. Okay, so now what we're going to see is that there's really 4 different types of diffusion that are going to be happening all at once. You have the diffusion force of the majority charge carriers trying to push them to the other side. You have the diffusion force for these majority charge carriers trying to push them to the other side, right? That's 2. But we have now 2 more, because now you can see there's a buildup of minority charge carriers right here, and so they're going to want to even out by pushing in that direction. Then the same thing over here. There's a buildup of minority charge carriers. They're going to want to push in that direction in order to even out. So we have 4 different diffusions happening all at once. So if we look at this slide here, we can see the buildup of the minority charge carrier concentration gradient as a result of applying VF. Now I used a straight line. It would really be more curved, but it was just easier to draw that way. And so again, right, this demonstrates how this gradient will cause the diffusion of the minority charge carriers that way and that way. If you take away VF, you end up back here. It kills the diffusion. If you apply VF again, it causes the buildup. So this is very much not a permanent process. That's the reason why once you forward bias the diode once, it's not like it conducts forever. As soon as you remove the voltage source, the concentration gradients will go away, the width of the depletion region will go back to what it was originally, and it essentially stops. Okay, so where are we in this process? We have talked about applying a voltage, the majority charge carriers cross over and become new minority charge carriers. And now we're going to see that these buildups will diffuse out. Eventually, they will recombine. The distance that they travel is defined by this constant we call LP. And remember that the current is not dependent on a single particle making it all the way from here over here. Okay, we're talking about net charge flow. So even though these particles go from here to here and then recombine, they're still contributing. Okay, it's almost like a relay race in terms of handing off. They're contributing to moving particles in the quote-unquote right direction. So all 4 of those diffusion forces together are sort of together adding up to create the current flow that we're going to see as the net in the end. So the process, and then after that we have more majority charge carriers that cross over to create more minority charge carriers, and the source adds new majority charge carriers. Anyway, you can see how the process continues on and on. Majority charge carriers come in, they cross over, they become minority charge carriers, they diffuse. They get rid of majority charge carriers, and then more are put in, and then the whole process just keeps going and going. So it's a little bit unexpected that a voltage source is sort of controlling the rate of diffusion, okay, even though diffusion current is not dependent on electric field. It's an indirect relationship, right, because the EMF is affecting the depletion region, and the depletion region is what is affecting the diffusion. So, funny enough, right, it's diffusion which is the governing current flow that we have within the pn-Junction, and not drift current, which seems counterintuitive given the fact that it's affected by a voltage source.
So the system wouldn't reach like an equilibrium unless you took it away?
Exactly, right. The source prevents it from reaching the equilibrium because it's constantly supplying new particles and essentially replenishing the concentration gradient over and over again. Yeah, but like if you do take it away, then everything returns back to normal, or back to the way it was in the open circuit. So now we have to ask ourselves the question, well, with so many things going on, how are we going to define the current flow? Right? Because the current flow is the rate at which these processes occur, but there's like 3 or 4 or 5 different processes happening. Essentially what we have to do is we have to figure out which one is the slowest. Okay, it's like if you're building a car, right? If you have a really fast engine, you have a really great body and really, tires that allow a high speed, but the transmission doesn't allow high speed, that's how fast your car can go. So same thing here with how fast this current can flow. We have to see what is the slowest process, and that's what dictates it. Now, as you would expect, the flow of electrons and holes from the source, that's fast. Okay, so that's not our limiting factor. And actually, the diffusion of the majority charge carriers across the boundary, that's also relatively fast. There's a lot of majority charge carriers, and the distance is small because really you're just moving across the junction. But the slow process is the diffusion of the minority charge carriers. Once the minority charge carriers are here and they emanate out, that's significantly slower than the other parts of the process. And so we define the net current of the pn-Junction based on that. And so that's what I said right here. Right? The limiting factor is going to be the rate at which the new minority charge carriers diffuse to recombine with the majority charge carriers. And so what determines this rate? A couple different values, Vf, and then the diffusion lengths themselves, Vp and Vn. All right, so now that we have a better understanding conceptually of what's going on inside of the pn-Junction, let's talk a little bit more about the mathematics behind it, because our goal is to get a VI relationship, right? We want to use the diode or the pn-Junction as a part of a circuit. And so, right, just like a resistor, V equals IR, we want V equals some function of I, or I equals some function of V. So how are we going to do that? What we need to do is we need to define the concentration of the minority charge carriers, and then from that we can define what the diffusion current will be associated with them. So here's what the minority charge carrier concentrations look like when we have the thing forward biased. Majority charge carriers go over here and push up the minority charge carrier concentration near the junction. Same thing on this side, okay? We can split this up into 2 different pieces. Pn0 is the thermal equilibrium value. So this box down at the bottom is the base concentration value. which is what you would have if you didn't apply any voltage. Then this piece of it gets pushed up the more forward bias voltage that we apply, the triangular part. So you'll see in the math that we're going to go back to 2 slides earlier, we are going to divvy up the minority charge carrier concentration into 2 pieces. We're going to call it the base concentration, and we're going to call it the excess concentration. And the reason why we're going to do that is because we're going to end up taking a derivative, and the derivative of this part is 0, whereas the derivative of this part is going to be not 0. Also, a couple things to pick out here value-wise. Right? Again, pn0 is the thermal equilibrium value of the minority charge carrier concentration. Pn at xn is saying what is the minority charge carrier concentration at xn. Xn is the edge of the depletion region. Same thing over here, np, minority charge carrier concentration at negative xp, and that's the edge of the depletion region. This is the maximum value, and then from here it goes down. So if you calculate NP at any other value of x, you would expect for it to be lower. Same thing over here. So really all we have to do in order to determine what the diffusion current is, take the derivative of these concentration gradients, multiply by diffusion constant and by the charge of an electron. So, so the value of Pn at the edge of the depletion region is going to have 2 parts, right? We'll have our excess and we'll have our base concentration. The base concentration is Pn0, and the excess concentration is Pn0 times e to the v over Vt, right? It builds up as the voltage gets larger. Now, this equation only gives us Pn at the edge of the depletion region, at x sub n. If we want to expand this for all x's, meaning we can get the value further to the right, we have to add the part that describes how it exponentially decreases with x. And so that is adding on this chunk. So this is all the part from before. And then now what we're going to say is that, so the base part is not affected by x, right? The base is always the same. It's a rectangle. The excess is times e to the minus x over x sub n over L sub p. All right? And so all that's describing is that exponential decrease in the concentration gradient of the minority charge carriers. That's the reason why we're using LP, even though we're talking about the n side, because it's the holes that we're worried about. And this equation is only describing 1/2 of what's going on. It's describing what's going on the n side, and we'll see that there's a similar equation that describes what's going on the p side. Okay, so anyway, this is the concentration gradient represented mathematically, and so all we have to do is take the derivative of this, and we'll have our diffusion current. So let's do that. We already talked about this picture. We already talked about the excess and the base concentration gradients. All right. So now what we do, eventually the diffusion current density associated with the minority charge carriers will be equal to negative Q dP times the derivative of the concentration gradient. So let's come up with that. The base part, the derivative of that is going to be equal to 0. It's a rectangle, so that goes away. And now all we have to do is take the derivative of this piece here. Essentially, everything to the left, this is all constant because we're taking a derivative with respect to x. There's no x's anywhere in here, so that just can get pushed out to the front. All we're really doing is taking the derivative of negative x over LP. And so what that does is that gives us an additional -1 over LP, which we multiply by all of this right here. And so that is our derivative. So the current density, the diffusion current density, is equal to whatever is shown here. Now, this equation shows us the current changes with what slice we're looking at in the PN junction. However, when we define the VI relationship for the diode for the PN junction, it should be a single value, right, that dictates from end to end what the current flow is. So like I said before, it's not imperative that a particle reach the terminal in order to contribute to the current flow. So the actual limiting factor, when we take a look at this right here, is going to be the maximum of this value. What is the maximum diffusion current that flows at the junction? So what we're going to do is we're going to substitute in an x sub n here, which will make this piece go away. So the maximum diffusion current density for the minority charged carriers on the n side, which are going to be holes, is equal to Q dp over LP, the base concentration value times e to the v over vt minus 1. And this voltage is where you're going to substitute in your VF. All right, so this is good. This is the equation that we have been looking for. The relationship between current density, we can multiply it by the cross-sectional area to give us current, and the forward bias voltage itself. Now we'll define a similar equation for the other side. We haven't done that yet, right? We've only been working with one side, so we can define a similar equation 338 for the other side. Same structure, different diffusion, constant diffusion length, and then obviously we're going to use the thermal equilibrium, the thermal equilibrium value for the N as opposed to the P. And then, to get the total current, all we have to do is sum the two together. So the total current will be equal to the cross-sectional area times the sum of the two current densities. Those are the two current densities. We add it all together. And yeah, I mean, that's really it. So this equation here and this equation here, because this is the form you'll most likely see later on when we get into chapter 4. The only difference between this form here and this form here is that we take a whole bunch of constants and we push them into IS, which is that same drift value from before. So IS is equal to cross-sectional area times charge of an electron, the intrinsic concentration squared, diffusion constants, diffusion lengths, and the doping concentrations. And this works for both the forward and the reverse bias regions. Because what happens when you apply a negative value here? This will get small, and you'll be left with negative IS equals I, which is, again, what you would expect to have in the reverse region, where the drift current, albeit a small value of drift current, will begin to dictate how the PN junction works. And so this is what we're going to call the exponential model for describing the behavior of a PN junction / diode. And we're going to use it a lot in future chapters, mainly chapter 4. Yeah.
V over VT substitute, what does that mean symbolically? Like, what is that voltage?
So yeah, the thermal voltage we described a while ago when we were talking about the Einstein relationship. Normally it's about 25.8 volts. So I mean, it scales the behavior of the exponential model. Obviously, right? The value of e to the whatever will be less than e if V is less than V over T. It essentially just scales how the thing works. But yeah, V sub T will be equal to 25.8 or 25.9 volts, depending on millivolts, depending on which what the temperature is and what the parameters are set for the example. Then the last question we ask here, so why is the diffusion current dependent on the concentration gradient of minority charge carriers? Essentially, it isn't. It isn't dependent on the original concentration of the minority charge carriers. It's dependent on the new charge carriers, which used to be majority charge carriers, which are then, before that, supplied by the source. So anyway, I just wanted to clarify that point. We can take a look at the exponential model, which is essentially the diode. It says that the current through the diode is equal to this constant saturation value times E to the applied voltage over the thermal voltage minus 1. And this is the shape of the VI curve. And this is a result of 2 classes worth of lecture talking about intrinsic semiconductors, doped semiconductors, the structure of a pn-junction, as well as how or what happens inside of a pn-junction in the open circuit, as well as the closed loop or applied voltage conditions. And so what we've done is we spent a lot of time talking about why this model makes sense or how it came about. We derived it from the physics. And so now we want to apply it. We're actually very close to the end of the chapter, so most of today is going to be on chapter 4 stuff. But before we end, taking a look at example 3.6. So example 3, we didn't do this last time, did we? No? Okay. So example 3.6 asks us to consider a forward biased PN junction conducting a current of 100 microamps with the following parameters. So we have our doping concentration values. We have our cross-sectional area. We have our diffusion lengths. We have our diffusion constants, and that's it. So first part, calculate what IS is. The most important constant when we're determining or looking at the VI relationship of a diode is IS, right? VT is normally known. It's a temperature-dependent value. So to calculate IS, we use this expression. If we go back to 340, we'll see that there's an equation based on all these values. All we have to do is plug in the appropriate numbers, and so we do that here. And I'm not going to go through and plug it into MATLAB because it's a pretty easy calculation, but you end up with 7.3 times 10 to the negative 15 amps as the saturation current. Okay, part B. Part B asks us to calculate the forward bias voltage using the exponential model. So we know the saturation value. Okay, we just calculated that. The current through the diode is 100 microamps. VT is 25.8 or 25.9 millivolts, depending on which one they make us use. And then V, this is the value we're looking for, which is the forward, or actually could be either, but the voltage across the diode. We know in this case it's going to be forward because the current is positive. So we go ahead and we start off with our exponential model. I equals IS, e to the V over VT minus 1. Now you'll see going from this line to the next line, we get rid of the minus 1. Now why is that? Well, the reason why we do it is because it makes solving the problem a little bit easier. The second question is, how can we do that, or why is it that we are allowed to do that? Just get rid of the minus 1. So essentially the rule for this is when V becomes significantly larger than VT, this term will blow up and 1 will remain relatively small, and so the 1 won't make a difference. So what we're going to say is that anytime the V is 10 times or more greater than VT, so about 250 millivolts, we are going to say it's okay to assume that the negative 1 or the 1 doesn't make a difference and get rid of it. So from this part here, we're assuming that the answer we get at the bottom is going to be larger than 250 millivolts, but we'll have to check that at the end. So once we make this simplification, then we can solve for V using this reversed or inverted expression. We take IS to the other side, we use a natural log, we multiply by VT, and that leaves us with our voltage. We plug in the values that we have, 25.9 millivolts. This is the 100 microamps, and then this is the 7.3 times 10 to the negative 15, and we end up with 605 millivolts, which is much larger than 250, or the 25, the VT, and so we're going to say, all right, that's fine, we can use that. If this value ended up being very small, let's say 40 or 45, 50 millivolts, then when we would probably have to revisit the first step and use the version of the expression with the -1, which you can. There is a way to solve that, but it's just algebra. It's a little bit different. Okay, and then the last part of this problem, it asks us to calculate the component of current due to hole injection and electron injection across the junction. So what does that mean? If you remember, when we derived these expressions, originally they were made up of two different parts, right? There's a component of the diffusion current that's associated with the holes, and there's a component of the diffusion current that's associated with the electrons, and they're shown separately here. And so what we can do is we can calculate those values separately, and that's what it asks us to do in the third part. And so for the solution, I only included the expression. We already have all these values. We know what V is. We know what the rest of the constants are. So you could plug in the values and get the number, but I just gave you the expression. This is homework 7, which is one of the two that I asked you to complete before we get back. And then here's the summary. So we're done with Chapter 3. I'll go through this really quickly, and then we'll jump into Chapter 4. So we talked about silicon, the importance that it has to microelectronics, the difference between intrinsic and doped semiconductors, with intrinsic being the pure and doped having impurities. We know that silicon forms a lattice structure that's defined by covalent bonds, the number of electrons it has in its outermost shell, which is 4 of 8. Silicon at room temperature or lower temperatures doesn't have that great of a conductivity value, and so it's not very useful for us in its intrinsic form. Now what we can do is we can add a doping agent and impurity in order to increase the conductivity, and the effect that has is, we either put in an impurity that has 1 more, so 5 valence electrons, or 1 less, 3 valence electrons in silicon, and that provides some additional charge carriers for current conduction. The more impurity that we place, the more we dope the silicon, the more conductivity or potential conductivity we'll have. We talked about two different types of current. We have diffusion and drift current. Drift current is associated with an applied electric field. Diffusion current is associated with a concentration gradient where we're trying to even out the concentration. And then we moved into the structure of a pn-junction, which is essentially just your p-type doped semiconductor put together with your n-type doped semiconductor and some terminals. And then we started out discussing how it works when it's open circuited, or when no external components are connected to its leads. And this involves the formation of the depletion region and all that type of stuff. Then we moved on to talk about the closed circuit operation when we apply an external voltage, how the forward bias differs from the reverse bias, and mainly the difference there is whether the polarity of the applied voltage agrees with the polarity of the built-in voltage. If it does, that's reverse bias. It makes the depletion region wider. If it doesn't, it's forward bias, and that makes the depletion region smaller, which ultimately allows diffusion to keep going and for current to flow. So although we apply an external voltage and see a current flow, it's not a drift current that's flowing, right? It's the externally applied voltage reduces the barrier, or the barrier associated with the depletion region reduces its width, allows diffusion to ramp up, and that's how we get our current flow. And then lastly, right, we end up with this after we define a mathematical expression for that diffusion current. We end up with our exponential model, which is the I equals IS times e to the v over vt minus 1. And you'll see that's going to lead us directly into chapter 4.